Okay, so we've already learned how to find and classify stationary points, but I'm going to work through one quick problem just to make sure that we have the process down. So to find our stationary points, it's the same process every time. The definition of a stationary point is a point whose first derivative is 0. So we are going to differentiate our function, and that means our first derivative is 4x cubed. And then once we found our first derivative, we're going to set that equal to 0 and solve, and that'll give us our stationary point, or points. And so we'll divide both sides by 4. We'll get x cubed equals 0, and when we take the cubed root of both sides, we find that x is 0. So in doing that, we found the first part of our ordered pair of our stationary point, but we've only found the first part. To find the second part, we are going to have to plug in 0 into our original function. Our original function is the function that gives us the y values of our coordinate points. So we have y equals x to the 4th, so we plug in 0. 0 to the 4th is just 0, and so we get the rest of our stationary point. So we have 0, 0. That process is always the same for finding stationary points. We're going to find our first derivative, and we are going to set it equal to 0. We're going to solve for x, and then whatever x values we get, we're going to plug into our original function to find the rest of our coordinate pairs. Once we've found our stationary point, we have to classify it. And so there's two ways to classify a stationary point. The first way is to do a concavity test with the second derivative, and the second way is to do a sign test with the first derivative. Now, I'm going to very quickly show us what it would be like to do our second derivative test. Our second derivative, first derivative was 4x cubed, so our second derivative would be 12x squared. And if our second derivative was greater than 0, if it was positive, then we would be able to say that it was concave up. And if our second derivative is less than 0, then we'd say that it is concave down at that point. Okay, and so we could plug in the x value of our stationary point, which is 0, into our second derivative. And if it's positive, then it's concave up. If it's negative, it's concave down. Now here's the only issue. In this example, when we plug in 0, we get 12 times 0, which is 0. As we know, 0 is not positive, and it's also not negative, so unfortunately that concavity test didn't tell us whether our function was concave up or concave down. And sometimes that happens. This is an example of that happening, and whenever that happens, we have no choice but to use the sign test. And so if we use a sign test, we're going to put the x value of our ordered pair, and then we're going to pick an x value to the right of that on our number line and to the left of that on our number line, and we're going to plug them into our first derivative. So our first derivative was 4x cubed, and we're going to plug that into our first derivative, and we're going to mark whether we get positive or negative. So when we plug in -1, we get 4 times -1 cubed, which is 4 times -1, which is -4. So we get a negative slope there. And then we're going to do the same thing, the button on the right, the number on the right, 4 times x cubed. We're going to plug it into our first derivative, and we get 4 times 1 cubed, which is 4, which is positive. So we can then see, we can get a visual idea of what's happening at the x coordinate of 0, because to the left of 0 we have a negative slope. At 0 we know we have a 0 slope, and at 1 we have a positive slope, so we can see that we have a local minimum. And so over here we can classify our point, our stationary point, as a local minimum. And so we can see right here, that's all the steps of finding and classifying a stationary point. Now, some people might say, well, do I have to do the concavity test if it's not going to work? Why wouldn't I just do the sign test? No, you don't have to do a concavity test. Sometimes one will work, and sometimes it won't, and sometimes one will be easier than the other. It never hurts to try one and then have to do the other. So now we're going to look at a good application problem of stationary points. So for this example, we're going to imagine right now that this is a non-calculator question. They've shown us the picture of this graph. Okay, so we're starting with this picture. We can tell that there's that local minimum right there. In fact, it looks like it's actually not just a local minimum, it's a global minimum. And so what we can do is, it's asking us to find the range of the function. And we know that the range of the function is going to be the lowest value, the lowest y value, and up from there, right? So in order to find the lowest y value, we can use stationary points to help us do that. So when we're looking at this function, this original function, f of x equals e to the x minus 2x, and at the first glance we might say, well, we have no idea how to find the minimum value. But since a minimum is a stationary point, we can say, oh, well, we can find that by using our stationary points. So we're going to find the first derivative and find the stationary point, because we know the stationary point is going to be that minimum point. So the derivative of e to the x is e to the x. The derivative of negative 2x is negative 2. So we are going to find that stationary point by setting the first derivative equal to 0. So we get 2 equals e to the x. And this brings our logs back into play. We're going to need to take a log base e of both sides, because log base e of e to the x is just x. That's what allows us to solve for x. And log base e is really just natural log of 2. So we now know that the x-coordinate of that stationary point is natural log of 2. Now we don't know what the y value is of that stationary point, but we can definitely find it by plugging into our original function. So here's our original function. And we're going to plug in natural log of 2. And e to the natural log of 2 is really e to the log base e of 2. That simplifies to just 2. And then 2 natural log of 2, we can't really simplify any further. So we now know the y value of our ordered pair is 2 minus 2 natural log of 2. Okay, and so we've now found that stationary point, because we're trying to find the range, which means we need to find the minimum. We know the minimum is a stationary point, and so we can find the stationary point by using the first derivative. And once we know the y value, we can say, oh, well, the range is from the y value, the lowest y value, which is the y value of that minimum, and above from there. So our range is going to be y is greater than or equal to 2 minus 2 natural log of 2. And if this were a non-calculator question, we would not be able to simplify 2 minus 2 natural log of 2 any further. Okay, so this is just a summary of our sign test. So we talked about how to do a sign test. We talked about how to do a concavity test. Here's our sign test right here. We're going to check the first derivative to the left of the stationary point. If it is positive, 0, negative, then that's a local max. Negative, 0, positive, then that's a local min. But what we haven't talked about is, and we've been kind of just touching on it a little bit here or there, that a positive and then a positive, or a negative and then a negative, is actually something that happens at our stationary points. And when we have the same sign on both sides of our stationary point, that's what's called an inflection point. Okay? And so inflection points are points where the concavity changes. So here I have the definition. An inflection point has the definition that there is a change in concavity. So let's go ahead and just draw something real quick. So if we are thinking about a change in concavity, if our function starts by being concave down, like that one is, and then it switches at some point to concave up, that is that point, wherever that point is that it switches from being concave down to concave up, that is your inflection point. And so it could also go the other direction. It could first be concave up, and then it could switch to being concave down, and whatever that point is right there where that change happens, that's your inflection point. And notice that makes a lot of sense with a sign test that we were saying that it would be positive, positive, or negative, negative, because right here we have a positive slope, a zero slope, and then a positive slope again. So in our sign test, we'll see that positive, zero, positive. Or we have a negative slope, a zero slope, and the negative slope again. So negative, zero, negative. So in our sign test, we see that something is an inflection point by having the same sign on our first derivative check. So I have that definition right there. An inflection point occurs when there's a change in concavity. Remember that a function is concave up when its second derivative is positive, and a concave down if its second derivative is negative. So one thing we should take note of is that the the slope on each side is going to be the same, but for the second derivative, the second derivative is going to switch from negative to positive or positive to negative. So at a point of inflection, what's really important is that if it's switching from concave down to concave up, then we have a negative second derivative to a positive second derivative, or from concave up to concave down, so we have a positive second derivative to a negative second derivative. That point where the second derivative is zero is your inflection point. So at any point of inflection, this is really important, any point of inflection, your second derivative is going to be zero. And it's not an if and only if statement. And so what I mean by that is that every inflection point will have a second derivative that is zero. But not every time that a second derivative is zero will be an inflection point. We're going to see some examples, don't worry. That's what I wrote right there. The converse is not true. Just because the second derivative is zero doesn't mean it is an inflection. Okay. And one of the examples of that is our last problem, where we had y equals x to the fourth, right? We had a second derivative that was zero, and so we couldn't do a sign test because we had zero. So we had to do, or I'm sorry, we couldn't do a concavity test, so we had to do a sign test. Okay, so this is all going to come together with some examples. So here we have our first example. Find the coordinates of the point of inflection on the curve, and so it gives us our curve. So in order to find the coordinates of a point of inflection, we are going to find the second derivative and set it equal to zero. That's your first step always. Okay? So our first derivative of this function is 3x squared minus 6x plus 5. Our second derivative of this function, 6x minus 6. Okay? And so in order to find the coordinates of the point or points of inflection, we're going to take that second derivative and set it equal to 0. And we're going to solve. So we found half of our ordered pair of a possible inflection point. Okay? How do we find the rest of that ordered pair? Well, if we know the x value, we're just going to plug that x value in for x into our original function to find the y value. And so that gives us 1 minus 3 plus 5 minus 1. So that gives us negative 2 plus 4 gives us 2. So that's a coordinate pair, and we think that there's a possibility that this is an inflection point. But just because we got that that's when the second derivative is 0 doesn't mean it is for sure an inflection point. We have to test it out. Okay? And so similar to finding stationary points, finding inflection points has 2 options. Again, one with the first derivative and one with the second derivative. So here are our options. Okay. My favorite way to check this out is to do the sign test as we know it with the first derivative. Okay? And so we take our first derivative, that's what we're going to use. And we take the x value of our ordered pair of our possible inflection point, and we're going to check. Remember that before, when we used the sign test with the first derivative, we were looking for it to either be positive slope and then negative slope, and that would give us a local max, or negative slope and positive slope, which would give us a local minimum. But in order for it to be an inflection point, it should give us either a positive slope and a positive slope, or a negative slope and a negative slope. So we're going to go ahead and pick a value to the left. I'm going to pick 0, and a value to the right, I'm going to pick 2. And we're going to check it out. So we're plugging that into our first derivative. And we get 5, so we get a positive slope. Now we're going to take 2 and also plug that into our first derivative. And that's going to give us 3 times 4 is 12, minus 12, plus 5. That gives us 5, which is also positive. We know that there's a 0 slope there. So we have a positive slope, a 0 slope, and then another positive slope. Couldn't really draw that real well. Let me try drawing that over here. Positive slope, 0 slope, positive slope. Okay? And so that is a point of inflection. The slopes on each side didn't change, but we know that we had a concavity change. Now, what's the other way that you could test this out? So let me start with this. If you did just this, you would be fine. You could be done, you could circle this, and you could say, that is my point of inflection. But let's say you didn't want to do a first derivative test, you wanted to do a second derivative test. That's totally fine. You can do that as well. We're going to do that right now. So if you wanted to do a second derivative test, it's going to look an awful lot like our first derivative test. We're going to put the x value of our ordered pair here. We're going to pick a number to the left and to the right. Okay. And remember that with the second derivative, we're talking about concavity, right? The first derivative is talking about slope. So over here, when we checked here, we had a positive slope and then a positive slope, which gives us that kind of shape right there, right? So that is a point of inflection. When we're doing a second derivative test, we're talking about concavity. So we should see a change in concavity, whether that's a positive second derivative and then a negative, or a negative and then a positive. That would represent a change in concavity. We have concave down and then concave up. So let's go ahead and plug this in. We're going to plug in 0 into our second derivative. And so we get 6 times 0 minus 6 is a negative. So a negative would represent what? It would represent a, let's see, it'd represent concave down. Okay. That would be, I'm just going to write concave down because it's a negative second derivative. And then we can also go ahead and plug in 2 into our second derivative. So that gives us 12 minus 6, which is 6. And so that is a positive. And a positive second derivative represents concave up. So that shows a change in concavity. So that shows that it's an inflection point. So when you're doing this, in order to find an inflection point, you're going to set the second derivative equal to 0. And you get your point, you get your x value, and then you plug it in to get your y value. Once you do that, you have to double check that it's an inflection point and not a stationary point. And the way that you can check that is either by doing a sign test with the first derivative, you're looking for the slopes to be the same on either side, or doing a sign test with the second derivative, and you're looking for the signs to change because that represents a change in concavity, and that would tell you that it's an inflection point. Okay, so let's look at another example. So it says if d squared y over dx squared equals e to the x times sine of x minus 1, find any points of inflection on y between 0 and 2 pi. So one thing that's important to note here is that they are giving us the second derivative. So we don't have to differentiate at all to find our points of inflection. We're just going to set our second derivative equal to 0. It's always our first step to try to find any points of inflection. And so they already gave it to us in factored form, so we can go ahead and split that because of the zero product property and say e to the x equals 0, sine of x minus 1 equals 0. Well, this says e to what power gives us 0, which is really like saying x is the natural log of 0, which doesn't exist. So we're not going to get any solutions from that. And then sine of x equals 1, that says where is sine of x equal to 1? Well, when we think about our unit circle, that's straight up here at pi over 2. And that's the only spot between 0 and 2 pi. So we found a possible point of inflection, and we can't be sure until we test it. So we have pi over 2 comma something. And really this problem should have actually said, we're going to go ahead and adjust this. Let's see, it really should have said, find the x values of any points of find the x values of any points of inflection. Why should it say that? Well, because we haven't learned anything about how to go backwards, and if we only know the second derivative, we don't know their original function, we can't find the rest of the ordered pair. So we think that there is an inflection point at pi over 2, but we can't be sure that it's an inflection point unless we do a sign test. And so we really have our choice of whether or not we want to do a first derivative sign test or, oh, I'm sorry, you know what? We don't really have our choice because we don't know what the first derivative is. So we have to do a second derivative sign test. I don't know what I was saying for a second. So we're going to plug into our second derivative, e to the 0 times sine of 0 minus 1. E to the 0 is 1. Sine of 0 is 0. So 1 times negative 1. So that is a negative second derivative, meaning that it is concave down. And then let's go ahead and try pi. So that's e to the pi times sine of pi minus 1. So e to the pi, sine of pi is 0 times negative 1. So that is negative e to the pi. So we get another negative, which means it is still concave down. So what does that mean? Well, it said find the x values of any points of inflection on y. We said the inflection point would be when the second derivative is equal to 0. We solved it out. We found that the only time the second derivative is 0 is when x is pi over 2. But then we did our second derivative sign test and found that the concavity didn't change. It was concave down, and then it was concave down. So what that means is that this was not a point of inflection. That means that there must not be any points of inflection. And so our final answer, when it said find any points of inflection, is that there are no inflection points. And our work there would show that. Okay, so lastly, I just have a summary of what we've been talking about. So there's two kinds of points that we've been talking about. Stationary points are whenever the first derivative is equal to 0, okay? And basically a stationary point could be a local max, it could be a local min, or it could be an inflection point. And so we can go ahead and classify a stationary point. And one of the ways to classify it is by doing a sign test with the first derivative. If we have a positive slope and then a negative slope, that's our local max. A negative slope and then a positive slope, that's our local min. Positive, positive, that's an inflection. Negative, negative, that's an inflection. The other way to classify a stationary point is to use the second derivative. If the second derivative is positive at that x value, then it's concave up, which means it's a minimum. If that second derivative is negative at that x value, then it's concave down and means it has a maximum. Now for inflection points, we can identify inflection points by taking our second derivative and set it equal to 0. Solve for x. You can find the rest of your ordered pair by plugging it into the original function. The thing is, you can't assume that just because the second derivative is 0 that it is an inflection point. It could just be a local max or local min. So you have to check, you have to confirm it that it's an inflection point, and there's two ways to do that. You can use the first derivative and do a sign test. This is just like we did before when we said, oh, let's classify stationary points. Same exact idea. Test the left, test the right, and see. You're looking for it to be the same slope. Or you can do a sign test with your second derivative, and in that case, you're looking for it to go to have a change in concavity, so positive to negative or negative to positive. If you get the same, that means it's either concave up, or concave down, then that means there wasn't a change in concavity, and then it's not an inflection point, which means it must have been a local max or a local min.